if f of x is equal to ln of x, then the inverse of that will be f inverse of x equals the exponential function. Okay. So that way here we know that the natural log of this function is equal to x, and the other way around, the exponential of ln of x is equal to x as well. In addition, we can establish a lot of the properties for this function just from this assumption that we're making exp. Notice here I'm writing it as exp, or exponential function of x. Our goal here will be to show that this is a function of the form e to the power of x, where e is a positive constant. And this will essentially be how we look at the inverse of ln of x. It's this function e to the x. It's called the natural exponential function. So to define it, we'll say the number e is the real number that satisfies the integral from 1 to e of dt over t is equal to 1. So notice that here, what we have is the integral from 1 to e. So e being this number that we're satisfying here of 1 over t dt is equal to 1. Well, that's what we're saying here is that ln of e is equal to 1. So what we're thinking of here is e is this number. We have this function 1 over t. So e is this number where the area between 1 and e, whatever it is, under the curve of 1 over t dt, the area of this region here is equal to exactly 1. So we're defining e in this way because, of course, what it does is it shows us here that ln of e is equal to 1. So that's an important property here. So with this, we get our e to the power of 1, right, equals, well, I'll say it this way. If I apply the exponential function here, so if I do the exponential of ln of e, we know that this is going to be the exponential of 1. So that shows me here that here, of course, we know exponential of ln of e will be equal to e. Okay. And so what we can essentially establish from there is that, yeah, so the inverse of ln of x is e to the x. So these guys can be rewritten in their inverted forms, but so actually what we're doing here is we're essentially rewriting the same equation just in different forms. Y equals e to the x is the same as x equals ln of y. Okay, and let's explore some properties of this function here. For one, we know that because they're inverses of each other, just compare the functions here. Like we've kind of already looked at the graph of ln of x a moment ago. Like we know it has this shape here. And so the function e to the x will look more like this. And we notice it has that sort of symmetry that we expect to see when we have inverse functions. They're both symmetric with respect to the line y equals x. So for the graph of e to the x, we notice that the domain is all real numbers. And the range is only positive numbers. Versus here, it's the other way around. Domain is only positive numbers, and the range is all real numbers. Notice here that as x goes to negative infinity, the graph will go to 0, right? So we can describe that as the limit as x goes to negative infinity, we get 0. Right, as it goes to the left, we see we get 0. And the limit as x goes to positive infinity, we notice as it goes to the right, the graph is going to blow up. It's going to go to positive infinity. And sort of analogously over here, we see that the limit as x approaches 0 from the right, as x gets closer to 0, the graph is going to go to negative infinity. And the limit as x goes to infinity is infinity. Okay. Excuse me. So let's look at a couple of other properties. Of course, these first three properties are just properties of exponential functions. And then the last two here are properties of inverse functions. So ln of e to the x is equal to x for all x. versus e to the ln of x is equal to x only for positive x. Okay, because of course we know that ln of x can only be evaluated for positive x. Let's think about how the exponential function can relate to exponentials of a different base. So here, if I'm just using that property here, let me come back here. Notice here that any real number, say b, can be written as e to the ln of b. So that means that b to the power of x can be written as e to the ln of b to the power of x. So with that property, we get a way of rewriting an exponential of any base in terms of e. So here, basically, any base e to the b to the power of x can be written as e to the x times ln of b. Okay, this will have to come back to later on because we're not going to use it for now. So basically, this shows you that all the rules that we establish here for e to the x, in particular the derivatives and integrals of e to the x, can easily be extended to any base. So with that in mind, let's think about, oh yeah, so here's one other property, is this limit here, the limit as x goes to infinity of 1 plus 1 over x to the power of x. And let's think about what's going on here. So on the one hand, so I'm going to look at this in a different way for a moment. Okay, so let f of x equal to ln of x. Okay, so we already know by the way that we've established it that f prime of x is equal to 1 over x, and in particular f prime of 1 is equal to 1. Okay, so this is something that we've already established, but let's unpackage this in a different way. So we'll say, on the other hand, we can express f prime of 1 as the limit as h approaches 0 f of 1 plus h minus f of 1 over h. F of 1 plus h is ln of 1 plus h. Ln of 1 we know is 0. We know that this is 0 here. So this is just then the limit as h approaches 0, ln of 1 plus h all over h. And here I can exploit some of the properties of logarithms if I want to rewrite this as well, you can think of it as 1 over h times ln of 1 plus h. So then I can bring this into the logarithm as a power. It becomes a power of 1 over h. And we know that this is equal to 1 by what we set up here. Okay. Now, if I take both sides of this equation and put it as a power of e, I can write this as e to the power of the limit as h approaches 0 of 1 plus h to the 1 over h power. Oh, I'm sorry, there should be a natural log there. Ln of ln of 1 plus h to the 1 over h power. This should equal to e to the power of 1. And moreover, here I can write this as the limit. So if I want to bring the limit on the outside here, we can do that since we know exponentials and logarithms are continuous functions. So I can write this as the limit as h approaches 0 of e to the power of ln of 1 plus h to the 1 over h power. Notice that here, actually, e to the ln of whatever, those actually sort of are inverses of each other. So we know this reduces to just the limit as h approaches 0 of 1 plus h to the power of 1 over h. And we know that this is equal to e to the power of 1. So this is equal to e. Okay, so here's one way of writing it. That the limit as h approaches 0 of 1 plus h to the 1 over h power is equal to e. And another way of seeing it is I can do a little substitution. So if I let so coming back to this limit here, if I let x equal to say 1 over t, okay, then I have t goes to 0 as x goes to infinity. Okay. And so this limit is really equivalent to say, so as x goes to infinity, this is the same as the limit as t approaches 0 of 1 plus t to the power of 1 over t. Which we showed here is equal to e. So this is an alternate way to express the value of e, is to write it as the limit as x approaches infinity of 1 plus 1 over x to the power of x. So in fact, this also gives us a good way of approximating e. So notice that here as x goes to infinity, we can just plug in larger and larger values of x here, and we should get values that get closer and closer to the actual value of e. So, you know, E here could then be approximated by putting in a really large value for E, say 1 over, I don't know, a million, say 10 to the power of 6. That should give you something that gets really close to the value of E. And the bigger the value of X that we plug in here, we get closer and closer to E. And, you know, so let me just point out here. It's closer to E as X gets bigger. Like in this case, if I were to just plug this into my calculator, I'd get something on the order of, or something around 2.71, which is, you know, a good approximation up to 2 decimals. So here I'll say it's something around 2.71. So the actual value of E is fairly close to this value. In fact, here putting in a million gets me, you know, at least the first 4 or 5 decimals are going to be the same. So I think, yeah, here it's at least accurate up to 5 decimals doing this approximation. But anyways, let's focus on something that we want to get really comfortable with, which is now taking derivatives and integrating e to the x. Notice here it has a very easy derivative and antiderivative formula. And in fact, here we can easily prove it using what we already know, which is that, okay, so if I have, say, y equals ln of x, or sorry, e to the x, well, then we know we can interchange this and write this as x equals ln of y, just rewriting it in this form here. We know how to differentiate ln of y, so let's differentiate the two sides here. So on the left side, we just get 1. On the right side, we know the derivative of ln of y will be 1 over y. And then implicit differentiation here, because this is the y variable, we're going to multiply by dy over dx. So with that, we get dy over dx is equal to 1 times y, sorry. So dy over dx is equal to y, which we know is equal to e to the x. Okay, so that establishes here that the derivative of e to the x is just e to the x. So it's got a very easy derivative formula. And doing the antiderivative is just as easy, right? So the antiderivative of e to the x is also e to the x. So here we kind of get those two formulas here go hand in hand. They're essentially the they're essentially here the same formula just written in reverse order. So let's practice this derivative formula. find the derivative of 3e to the 2x minus 4e to the x plus e to the negative 3x. So here's what I want to think about here is if I've got something, so we know that the derivative of e to the x is e to the x. Well, what if I have something of the form, the derivative of, say, e to the, I don't know, u of x? Well, it's the chain rule would apply here. So we would do e to the u of x power times the derivative of u, right? Or maybe more specifically, because these are kind of all in a specific form here, suppose I have the derivative of e to the ax, where a is some constant. Well, then this will be e to the ax times the derivative of ax, which is just, ax. So a is a constant, so the derivative of ax is just a. So here, assuming here that a is a constant. So with that in mind, we can take the derivative of 3e to the 2x will just be 3e to the 2x times the derivative of 2x, which is 2. Right? Minus 4e to the x is just 4e to the x. Right? The derivative of e to the x is just e to the x. Or here, the derivative of e to the negative 3x will be e to the negative 3x times negative 3. So here we'll have 6e to the 2x minus 4e to the x minus 3e to the negative 3x. Okay. Here's another example. Notice here we've got a quotient, so we're going to have to use the quotient rule. So I will write this as, well, let's take the derivative of the numerator. So I'll write e to the t prime times the denominator without taking a derivative minus the derivative of the denominator. So I'll write e to the 2t minus 1 prime times the numerator without taking a derivative divided by the denominator squared. So with this, we get e to the t. The derivative of e to the t is e to the t. Minus, and then this part stays the same. So minus then the derivative of e to the 2t minus 1. That'll be 2e to the 2t. Because it's e to the 2t times the derivative of 2t, which is 2, times e to the t without taking a derivative, all over e to the 2t minus 1 squared. So what we can do here is just do a little bit of simplifying. I can distribute e to the t here. That'll give me e to the 3t minus e to the t. And then here minus 2e to the 3t. Let me see, what else can we do here? I noticed we could then combine e to the 3t minus 2e to the 3t. So that would be negative e to the 3t. Okay. Of course, you could leave it like this if you want. If you factored in a negative e to the t from the numerator, you could also write it like this. That doesn't necessarily make it any better, so don't feel like you always have to simplify like that. Just one extra thing you could do if you needed to. Okay, so just a little quotient rule there. Let's see. Here's an interesting example. Oh, this is not what I wanted. Let me fix this. Okay. Okay. That's what I wanted. The derivative of e to the cosine of pi x evaluated at x equals 1/2. Okay, so that means we're going to take the derivative first, and then we're going to plug in x equals 1/2. But notice here we've got the cosine of pi x inside the e to the x function. So we're going to do a little bit of chain rule. So think of this as like something of the form ddx of e to the u of x power. So it'll be e to the u of x times u prime of x, or the derivative of u. So here it'll be e to the cosine of pi x, and then times the derivative of pi x, or of cosine of pi x. Okay, so we'll evaluate this at x equals 1/2. Now let's take the derivative of cosine of pi x. So derivative of cosine we know is negative sine, so this will be negative sine of pi x. But then we're going to multiply by the derivative of pi x, which is just pi, right? Because it's a constant times x. And then all of that evaluated at 1/2. Okay, so we've got e to the cosine of pi times 1/2, so e to the cosine of pi over 2. And then times negative sine of pi over 2 times pi. Notice here that cosine of pi over 2 is 0. And sine of pi over 2 is equal to 1. Okay, so I'm left with e to the power of 0 times negative 1 times pi. Okay, so in the end here, I think we just get negative pi. Okay. And in the next example, we're also going to consider here the derivative and integral formulas that we've established so far. So let me take a look at the next example here. It says, write an equation of the line tangent to the graph of f of x equals 2x minus e to the x over 2 at the point 0, negative 1/2. Okay. So we're going to find the equation of the tangent, which means we want to find the slope of the tangent using f prime. Okay, so the derivative of 2x minus e to the x over 2. Well, derivative of 2x is 2 minus the derivative of e to the x is e to the x. So think of this as like a constant 1/2 times e to the x. So it's the same thing, 1/2 e to the x. And then evaluating it at 0, there's e to the 0 is 1. 2 minus 1/2 will be 3/2. Now we've got the slope of our tangent, and we've got the point where it passes through the curve. So our equation of the tangent line will be y minus negative 1/2 equals 3 over 2 x minus 0, just the point slope form there. And so I think you could write it also like y equals 3 over 2x minus 1/2. Okay, so this is finding the equation of the tangent line. What about the second part? It says find the points on the graph where the tangent line is horizontal. So how do I interpret that statement there? How would I find the points where the tangent line is horizontal?
Is it where y equals 0?
I'm sorry, could you say it again?
Is it when y is equal to 0?
Where y is equal to 0? Not quite.
Okay, all I know, I think it's like critical points or something like that.
Okay, so how do you find the critical points?
When the first, I think the second derivative is equal to 0.
No, you're
No?
right the first
Was
time.
it the
It's when
first
the
one?
derivative is equal to 0, right?
Oh,
So remember,
okay.
the derivative tells you the slope of the tangent line. And when the slope of the tangent line is 0, that means you have a horizontal tangent line. So we want to just solve when f prime of x is equal to 0. Okay, so when you see that, when solve where the tangent line is horizontal, we're just solving when f prime of x is equal to 0. Which we found f prime here was 2 minus 1/2 e to the x. So we'll set that equal to 0. And then we'll solve it out, try and solve for x. Notice here, I can move some stuff around. So I'll subtract the 2 and then multiply or divide by the negative half. So I get e to the x equals 4 when I do this. So just moving some stuff around, I solve for e to the x, I get e to the x equals 4. So what's my solution for x going to be?
Is it like the natural log of 4?
Yeah, exactly. Okay. So you see horizontal tangent occurs at the point where the x-coordinate is ln of 4. If I were to evaluate f of ln of 4, that's 2 ln of 4 minus e to the ln of 4 over 2. E to the ln of 4 is just 4. Yeah, so it's 2 ln of 4 minus 2.
Professor, why exactly is it 2 ln of 4 minus 2? Or
So all I did was I went back to the original f, and so it's like I'm finding the y-coordinate on the original f by plugging in ln of 4 for x. So I go back to the original f and I plug in ln of 4 here and here for x. Right, so I got 2 times ln of 4 minus e to the ln of 4 over 2. And then using the property of logarithms, we know that e to the ln of 4 is just equal to 4. Okay. So this part here simplifies to just 4. Okay, so that's how I get 2 ln of 4 minus 2, as that's like the y coordinate. So that's like our f of ln of 4 here. Okay. So any other questions about that one? Well, let's practice some of the integration stuff here. Keeping in mind here that the integral of e to the x is also just e to the x. And I kind of want to point out here, you've got e to the 10x. And if we substitute 10x, let u equal to 10x, and of course we get du is 10 dx. So we get a 1 over 10 du is equal to dx. So the doing this substitution here, we get the integral of 1 over 10 e to the u du. So it'll be 1 over 10 e to the u plus c. And then putting the u back in, u is 10x. So this is just 1 over 10 e to the 10x plus c, which we can perhaps even generalize this a little bit more. If I have an integral of the form e to, say, kx, where k is any constant. Well, the same approach that we did here is going to give me the sort of analogous version of this, which is if I let u equal to kx, then du is k dx, and then I get a 1 over k comes from that substitution there. And then the integral of e to the u will just be e to the u, so I'm going to wind up with e to the kx plus c. So that's sort of a more general version of what we just showed here. Where here, of course, k is a constant. Okay, so let's see. Here's another example with an integral. What do you guys suggest I do here? Is there anything that comes to mind when you see something like this? Or is there a substitution that you guys think would be an obvious thing to do here?
Wouldn't you like substitute the bottom, the denominator?
Good. And okay, so the strategy here then would be to notice that when I take the derivative, we're going to get exactly what we see in the numerator, e to the x dx, right? Because we get the derivative of 1 plus e to the x is just e to the x. So here the e to the x dx that I have in the numerator just becomes du. So I'm going to get 1 over u du.
Can you also leave it as like natural log of u?
Yeah, and now this one exactly we know is the integral ln of u. And putting the u back in, we get our final result. So this is a good thing to notice is that when we're substituting expressions with e to the x, the derivative is e to the x, so we get things like this where it's got the e to the x upstairs like this. Will simplify nicely once we do that substitution. So here's one last thing here that I'll show you guys. I think this is the last example, yeah. So something called logarithmic differentiation. And what I want to show you guys is that we can take advantage of the properties of logarithms to help us simplify expressions like this. Because looking at this is very complicated. If I were to do the derivative, doing this directly, if I were to work out the derivative directly, requires several rules. For instance, we know we've got a product there in the numerator, so it requires product rule. We've got a quotient, so it also involves the quotient rule. And in addition, it's got this power 4 here, so it's some chain rule as well. So it gets very complicated. However, we can exploit the properties of logarithms. In particular, we know that with a logarithm, ln of a product, x times y, can be split up into ln of x plus ln of y. We know that now differentiating a sum is going to be much simpler than dealing with the product. So when we have a product, the logarithmic differentiation will change it into something where we no longer have to use the product rule. Or if I've got a quotient, say ln of x over y, well, I don't have to use the quotient rule because I can write this as ln of x minus ln of y. Or if I've got a power, say ln of x to the power of r, I can bring the power out as r times ln of x. So if I start by applying ln of x to both sides, we can exploit these properties here. In particular, I noticed that here we've got the product x squared plus 1 to the 4th times e to the x, and then divided by x squared plus 4. So let's start by splitting it up as ln of x squared plus 1 to the 4th plus ln of e to the x, and then minus ln of x squared plus 4, just using those properties there. And I could go a little bit further now because I've got the 4 here can come out. So this is 4 times ln of x squared plus 1. Ln of e to the x, actually that simplifies to just x. So that's using, again, property of ln of e to the x minus ln of x squared plus 4 here. So in a sense here, let me actually write this instead of ln of f of x, I'm going to write this ln of y. So we can now find dy dx implicitly using implicit differentiation. So now use implicit differentiation to solve for dy dx. Okay, so we know derivative of ln of y is 1 over y dy dx. Here we've got the derivative of ln of x squared plus 1, so I'll have 4 times 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x, plus the derivative of x is 1. And here minus 1 over x squared plus 4 times the derivative of x squared plus 4, so times 2x. Notice here I didn't have to use product or quotient rule anywhere. So it actually made it very simple. Okay. Now I can just solve for dy dx. So now just solve for dy over dx. And let's see, we get dy over dx equals, or I'll multiply y to the opposite side. And then here we've got 4 times 2x is 8x. For x squared plus 1, and then minus, here we have 2x over x squared plus 4. Okay, and then to get the final answer here, I'm just going to input replace y with the original f of x. Because here, actually, what I did was I remember f of x, I just wrote f of x as y to make it a little bit simpler. Okay, so that gives me the final answer here would be our original f of x squared plus 1 to the 4th, e to the x over x squared plus 4 times all of this.